In this lecture, we continue with several examples of solving initial value problems using Laplace transform. In this part, we consider examples that involve completing the square. So as a result, the solution to the initial value problem contains trigonometric functions. So our first example is the following initial value problem. Y double prime minus 4y prime plus 5y equal to 0. Y0 equal to 1. Y prime 0 equal to negative 2. You may pause the video and try yourself by taking Laplace transform of both sides of the equation. We have Laplace transform of the left side, which gives us Laplace transform of y prime minus 4, Laplace transform of y prime plus 5, Laplace transform of y equal to Laplace transform of 0. Now using the formula, Laplace transform of y double prime is s squared times Laplace transform of y minus s times y0 minus y prime 0. And we get s squared Laplace transform of y minus s, and y0 is 1. Y prime of 0 is negative 2. So we get s squared Laplace transform of y minus s plus 2. On the other hand, Laplace transform of y prime is s Laplace transform of y minus y0, and we get s Laplace transform of y minus 1 because y0 is 1. Now we plug into the equation. So plug into the equation star that we obtained by taking Laplace transform. This is I didn't mention Laplace transform 0 as before, it's 0. We have Laplace transform second derivative, so s squared Laplace transform of y minus s plus 2 minus 4 times in parentheses s times Laplace transform of y minus 1 plus 5 Laplace transform of y equal to 0. As before, we need to distribute in and keep all the terms with Laplace transform on one side. As we rewrite those, 4s Laplace transform of y plus 5 Laplace transform of y equal to this minus s over here becomes plus s on the other side, and then we have 2 distribute minus 4 minus 1, we get plus 4. So 2 plus 4 give us plus 6, and we move to the other side, minus 6. Now factor out the Laplace transform of y, we have s squared minus 4s plus 5 equal to s minus 6, and so Laplace transform of y is s minus 6 over s squared minus 4s plus 5. As before, we need to find the partial fractions. The first thing is to try factor the denominator, but it turns out we won't be able to factor this, meaning that the denominator is irreducible. We cannot factor. So we need to complete the square. Recall the formula. If we have s squared plus b times s plus b over 2 squared, which is the same as b squared over 4, then we have a complete square s plus b over 2 squared. And in fact, if we have a minus, then the same thing happens here. Just a minus in the middle. So to complete the square of the denominator above, s squared minus 4s plus 5, we need to split the 5 here into the sum of two numbers, so that the first 3 terms give us a complete square. In this case, b is 4 with the minus sign, so b over 2 is 2, 2 squared is 4, so we have 4 here. Or you could try anything you're more comfortable with to make sure that the first 3 terms give us a complete square. And whatever left, so 5 should be split as 4 plus 1. The first 3 terms give us a square. That's what it means, completing the square. So s minus 2 square plus 1. And so the partial fractions have the following form. I'm going to rewrite the Laplace transform of y, which is s minus 6 over s minus 2 square plus 1. Should be written as a times s minus 2 plus b, or divided by s minus 2 squared plus 1. Now this type of partial fraction is slightly different from what you may have seen in your college algebra. We use a times s minus 2, and s minus 2 because over here we have s minus 2 square, which comes from here as well. And we saw in the previous lecture that the reason we do a times s minus 2 is later on we can use the table of Laplace transform. But once we have that, clearing the denominators, give us s minus 6 equal to a s minus 2 plus b. Then we can solve for a and b. You can use any method you prefer here. You can distribute in and equate the coefficients, or you can set special values, say s equal to 2. Then you can have the value of b, and then s equal to 0 to solve for a, whichever way will work. So, turns out a is 1 and b is minus 4. So we have Laplace transform of y in partial fractions is 1 times s minus 2. Let's split it into this. And then b is negative 4 divided by s minus 2 squared plus 1. Now 1 is actually 1 squared. So if you prefer, we could do like this. S minus 2 squared plus 1 squared over here. Minus 4 times 1 over s minus 2 squared plus 1 squared. By using the table of Laplace transform, the first piece is s minus alpha divided by s minus alpha squared plus beta squared. The inverse Laplace transform gives us cosine and give us e to the alpha x cosine beta x. The second one here is of the form e to the alpha x sine of beta x, but beta here is 1. Taking inverse Laplace transform, give us y is the inverse Laplace transform of s minus 2 over s minus 2 squared plus 1 squared minus 4 inverse Laplace transform 1 over s minus 2 squared plus 1 squared in the denominator. And as I said earlier, we have e to the 2x cosine x. Beta is 1. 4 is a 2x sine of x. This is solution to the initial value problems that were given at the beginning. Now let's consider another more complicated example. Solve y double prime minus 2y prime plus 5y equal to 4e to the negative x. And now we have a non-homogeneous equation. Y0 equal to 0 and y prime 0 equal to 1 as the initial conditions. Again, such examples are familiar. We have seen something like this in chapter 3. And in that time, we will need to solve for y1, y2, and then solve for capital Y, and use initial condition to solve for C1 and C2. This is a long process as well. The Laplace transform is not much simpler either, but it gives us a different way to do it. So taking Laplace transform of both sides, then we have Laplace transform of second derivative minus 2 Laplace transform of first derivative plus 5 Laplace transform of y equal to 4 Laplace transform of e to the negative x. Then we use the formula. Laplace transform of second derivative is s squared Laplace transform of y minus s times y0 minus y prime 0, which give us y0 in this problem y0 is 0, so we don't have that, and y prime is 1, or minus 1. Similarly, Laplace transform of y prime is s Laplace transform of y minus y0 as well, and so s Laplace transform of y minus 0. We also have the right hand side, don't forget that. For Laplace transform of e to the negative x, we have 4 divided by s minus negative 1, it is plus 1. Remember that Laplace transform of e to the alpha x is 1 over s minus alpha. Alpha is negative 1 here. So put everything together and plug things into equation star as usual over here. And do the algebra. So we have s squared Laplace transform of y minus 1 minus 2 times s times Laplace transform of y plus 5 Laplace transform of y equal to the right hand side 4 over s plus 1. Distribute in and keep all the terms with Laplace transform on one side. Then we have s squared Laplace transform of y minus 2s Laplace transform of y plus 5 Laplace transform of y equal to the right hand side 4 over s plus 1. But don't forget, I will have other terms on the left side as well, minus 1, and that's all. Right? We bring to the others to the right side plus 1. Simplify this. We think of 1 as 1 over 1, and then you use common denominator. Factor Laplace transform out, we have s squared minus 2s plus 5 equal to, you should be able to do this and to get s plus 5. Now, solve for Laplace transform. We have s plus 5 divided by s squared minus 2s plus 5 times s plus 1. As usual, we need to do partial fractions. First, we need to factor the quadratic formula here, s squared minus 2s plus 5. But we won't be able to do this. We won't be able to factor. Instead, we need to use, we need to complete the square. So s squared minus 2s plus 5 as before. We need to split, find to the sum of two numbers. In this case, excuse me, for the first three terms to make a perfect square, we need to plus 1, and then the last number is 4. We get s minus 1 squared, and 4 here is 2 squared. So now the partial fractions has the following form. Let me rewrite first s plus 5 in the numerator, and then s minus 1 squared plus 2 square here times s plus 1. We have the linear piece s plus 1 and the irreducible quadratic terms. The partial fraction has two pieces. Let's do the linear first because that's easy. Just have a divided by s plus 1. For the irreducible quadratic, we have this. So it's going to be times s minus 1 plus c. Again, we need to have b times s minus 1 because we have s minus 1 squared in there. Now, clear denominators. We have s plus 5 on the left hand side, and for a we have s minus 1 square plus 2 square plus b times s minus 1 parenthesis plus c, and the entire parenthesis here times s plus 1. Recall that in order to clear the denominators, we need to multiply everything by the common denominator here, which is a huge expression which contains the quadratic form times s plus 1. Do the algebra carefully. Now we're going to set, say, s equal to minus 1. And I will have 4 on the left hand side equal to a minus 1 is minus 2 square plus 2 square. We put minus 1 in, we have b times negative 2 plus c, but then it would be 0 because s equal to negative 1. So from here we can solve for a. 4 equal to 8a, which give us a is a half. Now next, we can set s to be 1. That's another special values, because when s equal to 1, we will kill off this b times s minus 1. On the left side, we have 6 equal to a times 2 squared is 4 plus, and I said b times 0 plus c. Here we have 2. A is a half, and c times 2 here. So we get 6 equal to 2 plus 2c. So c is 2. To determine the value of b, we could use any values of s because we don't have any more special value. Or we could compare the coefficients of s squared. If we compare the coefficient of s squared, then on the left side there is no s squared, so 0 s squared. But on the right side we have as squared. If you distribute in, you will have bs squared. So equating the coefficient of s squared, equating as I said, we don't have any s squared on the left hand side, but on the right hand side we have as squared plus b s squared. So from here, 0 should be a plus b, and we know that a is a half from above right here. Um, so b is negative a half. Now we have the partial fractions or Laplace transform of y. Let's go back here in the format of partial fraction. A is a half, so we have a half divided by s plus 1. Half s plus 1. Plus b is minus a half times s minus 1 plus c. C above is 2. And all divided by s minus 1 squared plus 2 squared. And we need to use the inverse Laplace transform to solve for y. First, let's split for the quadratic, irreducible quadratic. We need to split into two pieces. One will give us cosine and the other give us sine. Minus a half s minus 1 over s minus 1 square plus 2 square. Then plus 2 divided by s minus 1 square plus 2 squared. We'll take inverse Laplace transform. You may pause the video and try yourself. We have a half inverse Laplace transform of 1 over s plus 1 minus a half inverse Laplace transform s minus 1 divided by the denominator. And lastly, 2 inverse Laplace transform of this. The first one is familiar, e to the minus x. Now for the last two, recall this. We have the first piece, we have the s minus alpha divided by s minus alpha square plus beta square. The inverse Laplace transform is e to the alpha x cosine beta x. I realize that this may be curly bracket here may be confusing, so let me just erase. On the other hand, we have beta over s minus alpha square plus beta squared, and the inverse Laplace transform is e to the alpha x sine of beta x. So using these two formulas, you should be able to write down the final answer. Erase this part right here and give the final answer below. So our answer is y, we have a half e to the minus x, and then minus a half times the inverse Laplace transform of this piece gives us e to the x cosine 2x. And then plus 2 times the inverse Laplace transform of this. Now in the formula, we're supposed to have beta in the numerator, but here we have beta just 1. We need to divide by beta in order to use the formula. So it's gonna be a half, beta is 2, so a half e to the alpha x sine beta x, which means a half e to the x sine of 2x. There's a 2 in front already. We have half e to the x sine of 2x. So finally, the answer is this. Plus e to the x sine of 2x. And this is the solution to our given initial value problem. Now you see that it's a little bit tricky when it comes to e to the alpha x sine beta x. So you need to be careful. And this is the end of the lecture.